So this session, we are going to be talking about optimizing Zephyr for peak performance. Now, as you can all see, one of the things that you are all probably here for a very important reason is that you've probably noticed that Zephyr is or will rule the world, right? In the embedded systems industry, I've seen over the course of the last several years, more and more companies adopting the use of Zephyr. And so I think this is actually a great thing. There's certainly been other open source real-time operating systems, or open source, right, that have been available, but none of them really have the drive or interest or the community that really Zephyr has behind it, which I think has made it extraordinarily interesting. And right now, Zephyr is certainly at a point where it's snowballing. In just about every industry that I work in as a consultant, everybody is looking at Zephyr as the RTOS that they're looking to go to. And it isn't necessarily just because of the RTOS itself, but because of the ecosystem that's around it. And right now, it's really snowballing between the architectures that are available, the ecosystem that's surrounding it, the training, all of the community, everything that's going on there, all the different support of the different companies that are getting involved, and of course even the individual contributors, it's well beyond what you find in other open source projects. And so Zephyr has certainly taken off like crazy. Now, as we start to look at Zephyr and we start to think about optimization, I've seen that there's actually 3 different types of groups of people that are starting to adopt Zephyr. Now, the first group is actually hardware engineers. So can I see a show of hands of how many of you are hardware engineers? Anybody out there? Okay, we've got a small group of hardware engineers out there. Okay, perfect. And so hardware engineers, a lot of the ones that I talk to, they've been super excited about Zephyr because they can start at a very high level, test things out, and it helps them accelerate development without having to necessarily always get software folks involved. Okay, so that's been pretty cool. I've seen a lot of hardware folks jump on the Zephyr bandwagon, I'll say. You have your traditional firmware engineers. So how many of you are traditional firmware engineers? Okay, a lot more of us, okay, maybe half of us. Now, as you can see here, I've kind of allowed the firmware engineer to be a little bit like pulling their hair out. And the reason for that is that I found that a lot of traditional embedded software developers have a large learning curve that they fight with in order to kind of get up to speed with Zephyr. A lot of people are used to FreeRTOS, ThreadX, kind of very low-level real-time operating systems that don't have the full ecosystem and the full software stacks available that you find with Zephyr. And then, of course, we have the third group of people, which are the software engineers. So who's maybe a pure software engineer or coming from like a Linux side of things? Okay, I see a few of us. All right. So those are kind of our 3 groups. And the cool thing about Zephyr is that this does allow a programming paradigm that allows people who maybe traditionally aren't hardware developers or traditional embedded software developers to adopt and start to use Zephyr and create real-time applications. But when we start to look at that, and we look at these 3 different groups, you can see these are 3 groups that are trained in very different ways and have very different worldviews of how to build and develop embedded systems. Now, this is kind of what brings about the problem and why I'm talking about optimization today. And despite all of Zephyr's flexibility that makes it so powerful, it's also fairly complex. When I talk to people who are working with FreeRTOS or ThreadX traditionally, they look at Zephyr and they go, "Oh, there's so many abstractions and there's so much going on there, and it's not as efficient, or I can't make it work maybe as well as Zephyr." But the fact of the matter is, they can. It's just they haven't gone through the learning curve yet to understand what the things are that they need to do in order to work with Zephyr. People sometimes get confused with device tree right off the bat, or kconfig, or some of the other tools that are available to us. And so what ends up being the core result here is that we can't end up with unpredictable and inefficient embedded systems. And so what I really want to talk to you guys about today, and I am by no means an expert in Zephyr, just like maybe many of you, I'm getting up to speed on Zephyr just as much as everybody else. But I have been working with real-time operating systems for over the last 20 years. And so I'm going to share some of my knowledge on how to actually optimize real-time operating systems and embedded systems, looking at it from the perspective of Zephyr. And so we're going to look at how we can understand optimization, what we want to optimize, when we should be looking at optimization. We're going to look at application optimizations. So I really look at this as being 2 zones: application optimizations, Zephyr itself, and then how we can optimize interrupts and latency. All right. Now, there's a lot that I'm trying to cover here, and so what I've decided to do with this presentation is kind of give little pieces of overview, and then provide some specific tips that you guys can then try to use to optimize your Zephyr-based applications. Okay. Now, as we look at that problem, as I mentioned, my name's Jacob Beningo. I have been working in embedded systems for about 20 years now. I work as an embedded systems consultant, oftentimes helping people with their software architectures, training them, and also helping them improve their development processes. And so I do a fair amount of training around RTOSs and also just helping people improve the way that they develop embedded systems. I often say that I help them develop faster, smarter firmware is kind of the area that I help focus people in on. Now, for today, what we're trying to do is understand optimizations. And for optimizations around Zephyr, there's really two different spheres of optimization that you can look at. The first sphere is going to be the actual RTOS itself. So a lot of folks who are maybe have worked with FreeRTOS, ThreadX, other RTOSs out there, you want to make sure, you've always looked at those as almost, they're not bare metal, but they're very efficient real-time operating systems. And as it turns out, Zephyr is actually extraordinarily efficient itself, but we want to make sure that we're able to optimize the RTOS itself in three different areas. Okay, we want to look at memory, speed, and power. These are going to be the areas that a lot of people who are working in IoT devices are trying to balance. Now, for a traditional embedded software developer, some of the processors that people are using today, they don't feel like they're real-time processors or that they're resource constrained, right? In the last talk, we looked at the test setup that was used, and it was using an MCX N947, which is a really cool NXP part, but it's like a dual-core M33 part, extraordinarily powerful. And when I look at that coming from the first processor I ever used was a PIC16F84. It had it was like 4 megahertz, had 2K of flash, and like 256 bytes of RAM. So from my perspective as a firmware engineer, that's resource constrained, even 48 megahertz. But a lot of processors today do have a lot of power. And so we're going to try to bridge the gap of what some of the optimizations you can do are if you're working in a very, what I would consider not so resource constrained versus maybe something that does have something more like a 48 megahertz bus, maybe is limited to 128K of flash and, maybe, I don't know, 128K of RAM or something like that, right? So from the other perspective here, we want to make sure our RTOS is optimized. And on the other side, it's the application that really plays a big role also in our optimizations. And again, we want to optimize these in these three different areas. Now, we're going to focus in a lot on kind of memory and speed today. And there's just because we only have 40 minutes, there's not a lot of time to talk about power stuff. But as you can imagine, if you're optimizing for speed, where you're getting things done very quickly, if you can get the work done quickly, what happens? You can put the system to sleep and save power, right? And so some of these tricks I'll show you, they really do go along to optimize power as well. And certainly what we want to make sure that we're doing here is we want to make sure that each layer is cleanly optimized based on the needs of our system, okay? Now it's going to turn out that you don't necessarily always have to have the fastest RTOS, right? Or the one that maybe is the most memory efficient. It depends on your system. In consulting, unfortunately, when I get questions from people, they'll ask me something, and the obvious response I say most of the time is, it depends, right? It depends whether you're using that 48 megahertz processor or whether you have, one of the high-end Cortex M33s that have, 150 megahertz bus and 2 megabytes of flash space and 768K of RAM. It's just going to depend on what your needs are and what the actual system is going to be using, okay? So why do we want to optimize? First of all, we might want to optimize on memory if we have a resource-constrained device. While many of us might be working on open source projects, or we might be doing one-offs or doing very low volume production, there's a lot of teams today who are looking at Zephyr very seriously for putting them in medical devices, in automotive controllers, who are looking at IoT devices that are maybe going to track assets, that need to work in a very low power environment. And so as you start to look at these devices, they might be done in a very high volume. And so we want to make sure that we're able to actually balance the cost of these products if we're doing high volume devices. And oftentimes memory is one of those trade-offs that we look at that can save us maybe 50 cents or a buck in volume, right? From there, we certainly want to worry about speed. We want to make sure that the system is actually real-time, that's able to successfully complete its deadlines without having any major problems. Okay, we saw in the last talked a lot about jitter and being able to meet those real-time requirements and how you might not always be able to hit them every single time, right? There's a little bit of jitter in every task. So optimizing for speed can be actually really important to make sure that our systems meet their deadlines. Now, if I have a simple consumer electronic device where real-time, where if the deadline is missed or jitters a little bit, maybe it's not a big deal, right? But if I have something like a safety controller, Zephyr has been really pushing on the fact that they're aiming for safety certifications. Maybe it goes in a brake controller. When I hit that brake, I want to make sure that that thing responds within a deterministic time every single time that the system is running. And then finally, power. Optimizing for battery life so that a device in the field can last longer. I have clients who are working with Zephyr who their systems need to go out in the field and they need to stay alive for 2 years or more before they're maintained. If they have to go out and change batteries or have customers ship those devices back, that really cuts back on their profits and their ability to even run and be a business that's viable. And so we want to make sure that we're optimizing in these 3 different areas. And oftentimes, the reason that we're optimizing for this is it comes down to our business constraints. Okay? So keep that in mind. We don't necessarily needlessly want to optimize. There are certainly, sometimes there's a want as a software developer to create a nice, elegant solution that is optimized and perfect. But as we've seen from the Silicon Valley types that say, hey, no, we want to break things, get things done first, right? We only should be optimizing if we actually need to. Now, there's on this slide here, and I'll go through this pretty quick because there's a lot that I want to get into. But you can see here there's different areas where we may want to actually optimize. Certainly early in the design phase if it's going to affect the main performance of our system. Optimizing maybe our software architecture to ensure that it is able to meet our memory constraints, our speed, and our power needs. The sooner you can do that, the better in your system, just so that you don't have to go back and keep re-architecting and changing the way that your system works. Certainly during development, if you find that there are areas of your software that are maybe starting to become bottlenecks or starting to produce problems, you might want to optimize then. It's certainly, there are times where you're developing your system and you might want to actually be profiling the system. We're going to talk a little bit about that here in a little bit. Along with, of course, optimizing when symptoms actually do appear as part of your system. Now, there was actually a company that I worked for several years ago, and they weren't using Zephyr, but they were a low-power device that had to work within a medical device, like within hospitals. And it was a badge that people would wear, and the device had to last for 14 hours, okay? And what ended up happening was that they didn't size the battery properly for the electronics or the system, and when we actually got everything put together and ran it for the first time, we actually discovered that the battery life only lasted 4 hours, right? And so that's actually a pretty bad symptom right there of, oh boy, we have this system that won't go the full 14 hours for the design, it's actually only lasting 4. Now you might say, well, that's not a big deal, use a bigger battery, right? Except the mechanical team at that point said, you know what, we're going straight to production housings, and there was no room to actually put a better battery in. And so, you go in and you optimize, and by the time we were done, we were actually able to hit like 15 hours. But this just kind of gives you an idea there of, you have to watch for the symptoms that are popping up in order to make sure that you optimize. So only optimize when it impacts the correctness, performance, and power cost that are part of your requirements for your system. Okay, so that's maybe some examples of when and why we want to actually optimize. Also, when it comes down to business needs, right, or needs of our users and meeting their specific needs and use cases. Now, the first area I want to talk about here to optimize when we are designing an application using Zephyr is to talk a little bit about application optimizations. There's actually a lot of pitfalls you can come across when you are implementing an RTOS-based system. The first, of course, is you can end up with issues like task starvation. If you're not paying attention or optimizing the number of tasks you have, what their run rates are, how much CPU utilization you're using, you can actually end up in an issue here where you can see that by this hashing here, that these tasks here are actually being starved, which isn't a case that we actually want to be in. Another case is where perhaps if you don't design your threads properly, you can end up with priority inversions. Now what these can do is they can cause all kinds of problems where you can end up with tasks essentially being locked up or being blocked and not being able to execute in the time frame that they should based on their priorities. And so you can actually end up with a high priority task being blocked by a lower priority one. And again, this can break the real-time performance of your system and break the speed of it and make it so that you can't meet your deadlines. Another issue, of course, is that you can end up with deadlocks. This is going to be where maybe you have an incorrect order of grabbing mutexes, or you have multiple resources that multiple threads are trying to get access to simultaneously. And if you don't architect your system properly, you can end up with these deadlocks occurring, which will then again affect the speed and the real-time performance of your system. There's certainly other ones like jitter, stack overflows. There's plenty of other faults or potential pitfalls. But these are some of the key ones that we want to make sure that we take a look at and watch for. And if any of you, we're going to talk a little bit about tracing later, but I just want to point out on this slide that this is an example of what the trace diagrams look like if you're using either Percipio has a tool called Tracealyzer. And there's one called Tracealyzer View that's actually free for Zephyr folks to use. And you can actually get nice little diagrams like this that show where when and where your tasks are actually executing, where the context switches are. And I've found that this has been a pretty useful tool for me to be able to visualize what my application is actually doing. And so if you need to optimize, for example, for speed, this is a great way to be able to go in and see how your tasks are actually executing and identify where any potential bottlenecks might actually be in your software. Now, I know that there's a fair number of us who said that they were firmware engineers. How many of you are familiar with rate monotonic scheduling? Okay, so I see about maybe a quarter of the number of people who raised their hands before. So one of my recommendations for optimizing your software is to use a technique called rate monotonic scheduling. Now, there's different ways that you can schedule a real-time embedded system. You can do things like shortest job first. You can go with shortest response time. You can also use periodic execution times, or the periodicity of your tasks. And what I have found is that a lot of companies and teams aren't familiar with rate monotonic scheduling. And what periodic, and rate monotonic scheduling is this periodic execution time. What this actually does is it allows you to look at your tasks and figure out, based on the rate at which they need to run, whether they're actually schedulable or not. And so you can actually set the priorities of your threads based on the rate at which they need to run. And what this does is it actually provides you with a very nice mechanism to be able to successfully set the priorities of your system. Now you might say, well, what does that have to do with optimizations? Well, if you have the incorrect priorities for your threads, oftentimes what you'll end up with is certain threads taking maybe the CPU when they don't need to, and you can end up with task jitter, you can end up with potential starvations, or you can just end up with tasks not meeting their real-time deadlines. And so because of that, we want to make sure that we use techniques like rate monotonic scheduling to identify what the priorities of our tasks should actually be. And you can see here on this right-hand side, this is just a couple of examples of, here's an example of maybe a system with 3 threads and different rates. You can see here the different rates based on this, how you might set the priorities based on the different scheduling algorithm that you might select. For real-time embedded systems, we often use, like I said, the periodic execution times, which we often call rate monotonic scheduling. Now, this technique is actually pretty cool because it leads to a second recommendation for optimizations, which is you can actually verify your schedulability. So, you've probably seen or worked on systems where you don't really pay attention to how long your threads are taking to run, and you end up with all kinds of weird behaviors. You press a button and you have a slow response time, or you end up with interesting things like that happening. What you can do with rate monotonic scheduling, there are some assumptions here that you can see. That we assume that all the tasks are periodic. We might assume that that all the threads are independent and they don't interact with each other, and so on and so forth. But the idea here is that even a simple system that does have thread interactions, you can try to get a feel for the schedulability of the system. And so what we actually do to calculate this is we calculate the CPU time of each of the threads that we're going to have in our system. And so for that, we look at their execution times, and we divide it by their period for each thread, and then we sum all of those up. Now, many of you have probably heard over the years that, hey, if a system is using more than, let's say, 70 or 80%, let's say 70% of the CPU utilization, it's going to be really hard to schedule tasks in your system. Well, as it turns out, if you actually were to solve this equation for an infinite number of threads, you'd actually find that it works out to be about 69.3% CPU utilization if you have an infinite number of threads that are running in order to make sure that things are actually schedulable. Okay, so that's where that number actually comes from some of the old literature. But the cool thing about this is that we can actually look at our system and we can calculate kind of upfront whether a particular system is going to be schedulable or not based on the execution period and the run rate of that particular, or the runtime of each thread. Now you might say, Jacob, I don't know what my actual run rate or the execution time for my thread is, right? I've not written the code yet for that. That's where some of these trace tools come in. You can actually get reports that say how long your average minimum and maximum time is for a thread to run, and then you can actually plug it into these types of equations and determine whether your entire system is schedulable or not, or whether you're potentially running up against theoretical limits that could create bottlenecks in your application. And so I have found over the years that this is a pretty useful technique to use. And as I mentioned, you can actually come through here. For this example, you could take your execution times, your period, divide it to get your utilization here, and then you sum all those up. And then as you can see here in this example, this would be a schedulable application with these 3 particular threads with these particular parameters. Now, again, this is a useful technique, but maybe one of the best ones that I've used over the years, and it's probably been a decade or more since some of these tools started showing up, is actually trace your application. I've seen a lot of teams that wait until they are in trouble to start tracing their application. My recommendation is always to go and start tracing your application on day one. Make it part of your CI/CD process. If you're going to commit code, have it commit, have your CI/CD program run, have it pull trace data for you, have a report generated, or worst case as a developer, run trace tools while you're developing your software to understand what the new code you're implementing, what it's doing, what impact it has on the system. All right. Now there are several different tracing tools that you can use out there. One of the ones that there's several of them. One of them here on this slide, the example is Sager System View. This is one that uses their real-time tracing capabilities, and you can see here it's actually pretty easy to enable through kconfig and through your project config settings. And then their IDE will record events up here, and then it will actually provide you with a horizontal thread trace that will show you what threads are executing when, and you can kind of get a feel for how your application is behaving. From there, you can also then get some additional statistics down there. So this is pretty easy to enable within Zephyr. On top of that, you can also enable Percipio Tracealyzer, which provides some additional graphics, some additional reporting capabilities. There's also some open source trace tools. I don't use them very often, to be honest, because I've been using the System View and the Tracealyzer tools for so many years. But if you check the Zephyr documentation, there are a couple of open source examples that you can use as well. And even, like I mentioned, Percipio Trace View, I think they call it. It just came out like a couple months ago. They provide a free way to be able to trace data. System View you can use, I think, within a certain time frame to be able to pull this type of trace data. But you won't know whether you're coming up against these speed issues or need to optimize your code unless you're actually taking the data. Now, another trick that I would recommend for your application code is not to mix scheduling paradigms. Now, what do I mean by that? If you look at Zephyr, there are several different ways that you can schedule threads within the Zephyr framework. You can create cooperative threads. These cooperative threads have a negative priority, and basically these will trump any of the preemptive threads that maybe you have priorities of like 1 through whatever the maximum is. Okay, so the idea here is if you're going to use something like rate monotonic scheduling, you can use preemptive scheduling with it. It will calculate and work really well with what you're doing. But if you start using cooperative scheduling, those are going to, once they get the CPU, they're going to lock up the CPU whether there is a high priority preemptive thread that needs to run or not. And so one of my recommendations is that use the cooperative scheduling carefully if you're going to mix the paradigms, but I have seen teams already start to get a little bit confused when they start to mix the different paradigms, and I've seen them start to come up with issues where maybe the cooperative thread grabs the CPU and never releases it, and you end up with 100% CPU utilization for long periods of time, or strange things happening in the code, okay? So just be a little bit careful with those types of things. Just like generally I recommend the folks, if you want to make sure that your system's running efficiently, sometimes to try to optimize, people will say, well, why don't I dynamically change my threads, my thread priority on the fly, right? Maybe sometimes this thread needs to be a priority 5, and sometimes it needs to be a priority 1. And so they'll try to tune the thread priorities to get the best performance out of their system, right? Well, just because the APIs say that you can, doesn't mean that will actually help. If you actually look at some of the research and the literature that's out there, they've shown that there's actually very little, you can get a little bit of performance improvement by using dynamic thread prioritization like that, but it actually results in more bugs, higher costs, and delays in project deliveries. Okay, so I don't recommend that as an optimization technique. Okay. Another thing that you can do, and this is a technique that is really, this isn't for someone that has, this is for a resource-constrained device. Okay, this is something 48 megahertz, 128K of flash, limited amounts of RAM. When you design your application, as software developers, we might architect a system that has a lot of different threads, right? And breaking the threads up, the system up in a whole bunch of separate independent threads, makes a lot of sense. But in a resource-constrained environment, what you're going to find is that the more threads that you create, the more memory you're going to end up using. And so you can end up actually with more power draw. You can end up with the need for more memory, all because you have maybe too many threads. And this is maybe a poor example because there's only 5 threads in the system, but maybe combining some threads in a very resource-constrained environment. I've seen systems that have over 100 threads in the system, okay? And we'll talk about it in a little bit where, if you have 100 threads, you have to have a task control block, right? And every task control block is going to, use a certain amount of memory. And it could be, it's probably only 256 bytes of memory. But as you get to 100, multiply that by 100 or whatever, and very quickly you could start running through memory in a very resource-constrained environment. So make sure that you're very careful about the way that you architect your system. Make sure that you're not just overusing what's available. Hardware folks give us processing power, and us software folks tend to take it away, right? And so we want to make sure that we're very careful about how we architect our systems. And I have found that oftentimes you can combine and simplify your thread architecture, and that can result in saving RAM. Because a lot of times, just because you set a kilobyte of RAM aside for a particular, or maybe multiple threads, it doesn't mean they're both going to use that much. And sometimes combining them, you still only need a kilobyte of RAM for those two features to run together in a single thread. So keep that in mind. Some of the other things that I've seen from an application standpoint, and I've seen these recently, which is why I kind of mention these. Some of this might seem obvious to you, like, yeah, why would you do that? But at the same time, a lot of these examples come from me working with teams and consulting, and I see these things in the field, and I mention them to everybody just in case you're not aware of this. And this particular one is passing data by pointers. So what I will often see happen is that teams will actually go and they'll say, oh, well, I have a lot of memory. I'm just going to, I'm going to just copy the data from some source. Maybe I have a buffer that's a kilobyte. I take that data. Oh, I'm going to put it I need to get somewhere else, so I'm going to pass the data through a message queue. And so they pass the data into a message queue, and then on the other side, they have a thread that receives it, and that data is pulled out of and copied out of the message queue. Well, what ends up happening here is that you end up actually, when you do that, you end up with a kilobyte of RAM here, a kilobyte of RAM there, and a kilobyte of RAM here. And then on top of that, you end up with a performance hit because now you're copying data from this thread into the queue and then into the other thread that needs to be there, okay? And so in general, if you're gonna pass, I'll say 100 bytes or less, maybe it's only 32, depending on your system architecture, you can get away, instead of copying, in this example I have a kilobyte here, I have a queue size of 10, and so right there you could say my queue would have 10 kilobytes of RAM just to allocate enough slots inside of my queue for that much data. And so that's going to end up really using a lot of RAM. And like I said, wasting a lot in copy operations, versus where maybe instead we just go and we copy by pointer. All right, and so then the code down here is saying, no, you know what? We might have a local buffer, but instead all we're going to do is pass the pointer. And so instead of passing a kilobyte, we're passing 4 bytes of data as a pointer. Yes, then we probably need to have some way to protect the data right through a mutex, but that's much more manageable than the performance hit and the amount of RAM that we might use for copying directly the buffers over. So on top of that, when you're thinking about your application, again, some of these are kind of just general advice for working with real-time operating systems. Look at the primitives that you are using. Look at what it is that you're using in your application. Task control block has a lot of different stuff that goes with it. So every thread that you create, there's going to be a lot that goes into that task control block. On top of names, priorities, the actual pointer to the task code, and of course the stack, which is the larger memory usage from that perspective. Every semaphore you create, every message queue, every worker queue, every everything that you create is going to need some type of control block that's going to allocate memory. And all of these devices over time, there's overhead associated with using these. And so you just have to be cognizant that these things exist and that they could potentially affect the performance of your system. And so sometimes just minimizing the number of RTOS objects you have can make a difference in how well your system actually operates. Okay, some other things for us to look at here. Optimizing interrupts and latency. I know I've probably got about 10 minutes, so I'll try to go through some of these a little bit quicker here. Keep ISRs minimal and fast, okay? You might look at this particular code here on the left and say, actually, this doesn't look too bad. It's a pretty short function, right? It's only got 4 things going on inside of it. Well, I know most of you are firmware engineers, or half of you, so you kind of might look at that and go, uh-oh, this isn't good, because you can see here that inside of our interrupt service routine, while this looks like it's short code, we're actually going and doing a whole bunch of processing of the data inside the interrupt service routine. For any real-time system, again, to optimize performance, we want the interrupt service routines to run, grab the data, do whatever has to be done in real time, and then offload whatever else has to be done to some type of worker thread, or let it be ran at some point in the background, and essentially get out of the interrupt service routine as fast as we can. Now, the cool thing about Zephyr is that it does allow you to, it does keep track of your interrupt service routines, right? You can register interrupts with Zephyr. It manages them for you, which is pretty cool, versus like, looking at ThreadX or FreeRTOS, where those were always outside the context of the RTOS. But you can see here on the right-hand side, this might be a better way of writing this particular interrupt service routine. We keep it short, where we just pull the data here, and then we have a separate thread that's going to be a worker thread that's going to actually go through and process the data later. And certainly you might say, yeah, it's more lines of code, but it's going to be far more efficient and more optimized to be able to run that. On top of that, make sure that you use interrupt-safe APIs from the kernel. Not all APIs are necessarily going to be interrupt safe. So, for example, you don't necessarily want to be, you don't want to be taking semaphores or anything like that. These are all okay examples here. Giving a semaphore, putting things into a queue, that's all great. You don't want to do things like this on the right-hand side, where maybe you're trying to take a semaphore, where you're actually blocking the CPU or the kernel from doing other activities. Okay, so watch out for doing those types of things. Zephyr does have low latency interrupts that you can use. Now, what these are going to do is they're actually going to allow you to bypass the Zephyr's masking logic for time-critical ISRs. Okay, so they're going to basically be able to trump over other activities, other threads that are running in your system to allow the interrupt service routine to be executed as quickly as possible. We can do that using the IRQ Connect API there. From there, just in general, you have to enable that in your project config file. It's not something that is just available by default, so you do have to adjust some of the settings there in order to get that low latency available to you. Okay, so those are some examples of things you can do at your application level that you can do with interrupts and latencies. Some other things that we can do for Zephyr itself. Now, if you have a lot of power in your embedded system, on your microcontroller, optimizing the RTOS may not necessarily be a big deal. But if you're worried about low power design, you don't want your kernel to be taking up more CPU cycles than it needs to. In some applications, the RTOS itself may be using between 4 and 8% of the CPU compared to the application code. So it's a very much smaller percentage of it. But at the same time, you want to make sure that it is optimized so that it's not wasting clock cycles. So back in September, I actually did a comparison. I was saying, hey, I wonder how different open source RTOSs compare to each other, and I was curious how maybe commercial RTOSs compare to the open source ones. And so I went through and I compared FreeRTOS, ThreadX, and Zephyr and said, hey, how do these actually compare from a performance standpoint? Looking at thread execution, looking at cooperative scheduling, preemptive scheduling, how good is memory allocation, how well is it working for semaphores and those types of things. And I just wanted to get a feel for what the difference was. Now, kind of going through here, you can see in general there's some results here that I was able to pull back in September. And this is using Zephyr 3.7. So I'm going to warn you up front, just so that you guys don't pull out the pitchforks and the torches and come after me or anything like that, okay? But you can see here, with the setup that I use, I was actually using a STM32L475 IoT discovery board that I ran these measurements on. But you can see here, in general, a lot of the, there was a little bit of a difference between these, but in some of the cases, Zephyr, performed a little bit less performance-wise than maybe some of the other open source RTOSs that were out there. Now, as you can imagine, I said, don't get your pitchforks and torches out quite yet, because when I published that report, obviously there was some people not happy in the Zephyr community, right? But what that did was it kicked off improvements to the kernel. And so as part of Zephyr 4.1, there were a lot of improvements to the way that the kernel itself performed. And what you can see here is that preemptive scheduling actually improved by 46%. Synchronization improved by 36%. 24% faster message processing, among other improvements. There was also the inclusion, there's this new multi-queue scheduling paradigm that you can use that's experimental, that also provides some additional performance in certain areas. In a couple areas here, you can see it's maybe doesn't perform as well as your standard Zephyr 4.1. And this is experimental, so you actually have to go in and enable it yourself. And because it's experimental, we can probably expect changes to occur. But as you can see here, there were improvements that could be made to the kernel running as it was. And these were measurements that were performed by the Zephyr community. And on top of that, they took the thread metrics benchmarking harness, and they actually built that into Zephyr itself so that everybody can go through and they can actually do these comparisons on their own systems, and it's pretty easy to go and invoke that, and then you can actually compare it to free RTOS or whatever other things you might be comparing it to. But it gives you a feel for what you can actually what it actually does. And so these are really probably the latest comparisons of how Zephyr compares to other real-time operating systems. You can see here that with the improvements here, you can see here that Zephyr now in many cases has exceeded a lot of the other open source RTOSs that are out there, right? And maybe there's some areas where they're close, but for the most part, there's a lot of improvements that have been made there. And so you might be wondering, okay, this is great. What else can I do? Well, when I went through and started to figure out ways that I could, from that report that I put together, ways that Zephyr could be optimized, one of the big low-hanging fruits that I discovered was that when I did all my comparisons using GCC. And what I did was I also compared some that I had available with IAR, and I actually found that when you switch to a commercial compiler, you can end up with almost 20 to 40% improvement in the execution times of the kernel itself. And so you can imagine if you apply that to the kernel, to your application code, that can make a big difference if you're worried about improving and optimizing the speed of your system, okay? And as part of Zephyr 4.1 release, IAR is actually pretty easy to enable to switch there at the command line so that you can actually compile with IAR versus using GCC. Okay, so that is a commercial tool, so there are obviously additional costs there. So if you really need to optimize, keep that in mind. Some other things that I found by default, and these are good things, but they're also bad from a performance standpoint. By default, Zephyr will enable the memory protection units. Okay, so the MPUs are enabled by default. Okay, well that's good because people should be using the MPU. But at the same time, the MPU does give you with preemptive scheduling and some of the other areas, it actually can cost you 50% just by using the MPU. Okay, now depending on how secure your device needs to be and what your security strategy is, considering, you may want to look into how Zephyr uses the MPUs, and that could be a potential area to improve performance. Now again, MPUs, we often use them to protect memory, so they're very important from a security context, but I don't know, a lot of teams I work with, security is kind of a low priority compared to other requirements of the system. And so, I kind of mentioned that to you guys. So again, be careful about disabling the MPUs. It can be dangerous, okay, but again, from a performance standpoint, that's something that can affect how your system behaves. Certainly, the rate at which your system tick goes is something to look at. Certainly, make sure that you set your configuration for the compiler for speed. If speed is what you're optimizing for, if it's for memory, set it for memory. All right. Those are a couple things that you can look at. Certainly, you can turn off the runtime error checks as well. Zephyr in the kernel has certain checks that it does while it runs. Guess what? All those cool extra checks, they cost you time and performance. All right, so you want to maybe potentially look into those. Same thing with logs. Logging is fantastic. If you want to be able to get logs from your remote device, you certainly don't want to disable them. But again, for a production system, there is going to be extra overhead there for running logs, recording them, all that stuff. And so that's another thing you might want to disable. Same thing with your runtime assertions. If you disable those, you get extra performance out of the system. Now, some of these are the things that I disabled to ensure that I had apples-to-apples comparisons when I was looking at like free RTOS and ThreadX, because those operating systems don't have these things enabled by default. And so I kind of, as I dug in and compared the different open source ones, those were some things that I actually found could help with performance there. Another scheduling paradigm that you can look at within the kernel is actually turning time slicing off. In a lot of RTOSs, the time slicing feature is actually stuck. It's stuck in that you can't configure it very well. It's configured at just a single tick, and you can end up with a lot of context overhead where you're just switching back and forth between tasks, essentially for no reason. And so the cool thing is you can either disable it or you can enable it here within Zephyr and make that time slice a little bit longer so that you're not wasting as much time switching from one thread over into the next one. Okay. All right. So those were a few ideas that I had related to optimizing Zephyr. I know some of them are higher level best practices, but those are also areas where I've seen teams struggle to optimize their embedded systems. and even working with Zephyr that I've seen over the last 6 to 12 months. And so for you guys, those are some ideas for you to take back and look at. I certainly would recommend you look at the Zephyr documentation, dig a little bit deeper. Certainly, if you have other questions about optimizations, you can ask me afterwards, or feel free to email me at jacob@beningo.com. Always happy to share what I know about Zephyr, and certainly, as I mentioned, I'm no Zephyr expert at the moment, but I'm certainly getting up to speed and finding it to be a very interesting RTOS that I'm planning on using for a very long time into the future. So with that in mind, thank you, and hope you enjoy the rest of the conference.